Welcome to ClickMyProject.com. Let me discuss about the project performance analysis of time of arrival estimation on OFDM signals. Let me discuss about the abstract of the project. Orthogonal frequency division multiplexing is a method of encoding digital data on multiple carrier frequencies. OFDM has developed into a popular scheme for wideband digital communication used in applications such as digital television and audio broadcasting, DSL, Internet Access, Wireless Network, Powerline Networks, and 4G mobile communications. OFDM is becoming widely applied in wireless communication system due to its high rate data transmission capability with high bandwidth efficiency and its robustness with regard to multipath padding and delay. It has been used in digital audio broadcasting systems, digital video broadcasting systems, digital subcarrier line standards, and wireless LAN standards. OFDM is a frequency division multiplexing scheme used as a digital multi-carrier modulation method. Large number of closely spaced orthogonal subcarrier signals are used to carry data on several parallel data streams on channels. This paper uses Ziv-Zakai bound, which is tight in a wide range of signal to noise ratio values for a given signal bandwidth. A proper power distribution of the OFDM subcarrier is crucial for achieving a good performance in the low to medium SNR region, where the RMSE curve exhibits the typical threshold behavior. We discuss about the flow diagram for our process. Initially, the OFDM signal are going to be generated. Ubiquity of this communication technique has determined an interest in the OFDM technology, also in the field of positioning, where the intrinsic characteristics of the OFDM signal may be studied for understanding how to design a proper OFDM waveform suitable for pseudo-range calculation. Concerning this aspect, the estimation of the time of arrival of a signal is fundamental topic. Accordingly, the design of TOA-based positioning systems that exploit OFDM waveforms has been addressed in also analyzing the possibility to use band-limited multi-carrier modulations for achieving selective accuracy in global navigation satellite system. Proper shaping strategies for the OFDM tones have been further adopted for joint capacity maximization and TOA accuracy purposes in multipath channels. Next, the digital signal to analog converter. In the OFDM signal to be digital to analog generate to continuous time signal on the sampling interval. Impulse response of the DAC with denoting the with windowing functions that limits in time the sync interpolating functions. Thus, instead of using the widely adopted ideal model in this study adopts the realistic OFDM waveform, and hence considering the actual output of the DAC used function in Hamming window, the TOA RMSE performance of realistically modeled OFDM signal. Next, in the Cramér-Rao bound and Ziv-Zakai bound, the characterization is performed by properly shaping the power spectral density of the OFDM signal so as to infer the influence of the subcarrier power distribution of the TOA root mean square estimation error using the Cramér-Rao bound and the Ziv-Zakai bound model. TOA RMSE behavior is explored not only in the asymptotic region but also in the threshold region by introducing a novel quantity which is complementary to the widely adopted Gabor bandwidth. Finally, the trade-off between asymptotic and threshold performance is identified, showing that the GB is not only the parameter to considering for designing a TOA reference signal. In the RMSE error identification used, performance sphere effectively evaluates the RMSE threshold performance of a signal by properly locating the boundary between threshold and asymptotic region. Secondly, strongly influences the asymptotic RMSE performance since higher values of lead to an increase of the bandwidth occupied by the subcarriers with the same inter-channel spacing that ultimately determines an increased GB and hence a smaller asymptotic RMSE. Thirdly, the adapted value of subcarrier spacing strongly influences the RMSE behavior in the TR. Interestingly, the signal obtaining the best asymptotic performance shows the worst threshold behavior. A direct comparison between and shows a satisfactory agreement between the two definitions of the SNR threshold, further revealing that when the ZZB in the boundary between TR and AR is sufficiently steep, and the performance analysis of SNR and RMSE are performed. Two sets of power distribution of the available subcarriers have been defined to evaluate the RMSE performance both in the asymptotic and threshold region by using CRB and ZZB. Developed analysis has confirmed that for a given maximum bandwidth, the power distribution influences RMSE both in asymptotic and threshold region. Let me discuss about the running procedure for our process. Select the main.m file in the current folder, right-click that file and run for executing this process. Here we perform the OFDM signal generation followed by TOA and also RMSE estimation. And this is the OFDM signal transmitted signal. Initially we have generated. This is the continuous time signal, which is the output of the ADC, that is analog to digital converter. And this is the transmit spectrum of OFDM. For every subcarrier we have calculated the power spectral density. And this is the SNR for 10-bit ADC with the different RMS jitter values, SNR graph. And this is the figure 5 for our result. And this is the power distribution obtained using NC is equal to 72. Here UD for 72 and also cost function ONA for 72 have been obtained. And this is the normalized RMSE and corresponding bounds response. And this is the various SNR graph for our Ziv-Zakai bounds, selected distribution of ODNC, and also for the values of NC is equal to 72. And this is the zigzag bound for selected distribution of NC for values of NC is equal to 300 for various values of SNR graph. And this is the plotting response for jitter threshold and also for threshold for the distribution of UDNC and also cost function in NC and NC is equal to 72. This is the plotting response of jitter function of threshold and also beta threshold for the distribution of UDNC and also cost function in ANC and NC is equal to 300. Here we perform the volume transmitter followed by a TOA estimation using Cramér-Rao bound and also Ziv-Zakai bound. Here we estimated the root mean square estimation error response. Thank you.